All right, today we're ditching the textbooks and heading straight to the factory floor. We're going to follow a real-world crisis as it unfolds to see how the principles of air compression aren't just theory, they're what keeps a multi-million-dollar operation from literally grinding to a halt. That's a question most plant managers hope they never, ever have to answer. To really understand why, I want you to meet Alex. Alex is a plant engineer at a huge food processing facility, and their day is about to go from really bad to truly catastrophic, all because of one single overlooked piece of equipment. So, Section 1, a factory's air problem. Picture this. Alex is on the factory floor. Alarms are blaring everywhere. The production line, which was this perfect symphony of automation just minutes ago, has gone completely silent. Alex is smack in the middle of a full-blown shutdown, and the pressure is seriously on. So Alex is dealing with a double whammy here. First, the easy part. Pneumatic actuators are failing all down the line because the system's air pressure is just tanking. But the second issue, it's so much worse. Quality control has detected trace amounts of oil in the product. This isn't just a shutdown anymore. We're talking about a potential recall that could cost millions and wreck the company's reputation. Okay, so what do you do? A less experienced engineer might just run straight to the compressor room and start tinkering. But Alex knows better. The compressor is the heart of the system, sure, but the problem could be anywhere in the system's arteries. So the first step is a full system diagnosis. Alex knows better than to guess, so the approach is super methodical. First things first, you identify every single device that uses compressed air. Then you grab the manufacturer data and calculate the total potential demand. Of course, not everything runs at once, so you apply a load factor to get a more realistic picture of usage. And finally, the most critical step of all, conducting a system-wide leak test while everything is shut down. And this is where Alex has that aha moment. The leak test reveals dozens and dozens of tiny hissing leaks at joints and valves. I mean, individually they seem like nothing, but just look at this table. It shows you the staggering reality. A single 1/8-inch leak, barely noticeable, can waste over 740,000 cubic feet of air a month. It suddenly becomes crystal clear. The system is just hemorrhaging pressure and money. So, okay, the leaks explain the pressure drop, for sure. But what about the oil contamination? Now that Alex has a clear picture of the system's massive demand, which is way bigger than it should be because of the leaks, it's finally time to turn to the source of it all, the compressor itself. And here is the culprit. See, the compressor was sized for the original designed load of the factory, but after years of these tiny leaks adding up, the actual load is way, way higher. The machine is running constantly, 24/7, just to keep up, and it's overheating. And as it overheats, its oil-based lubrication starts to break down and get carried over into the airstream. That's our contamination. So a replacement is definitely needed. Let's look at the main options Alex is considering. This slide compares the two most common types of positive displacement machines. On one hand, you have your reciprocating compressor, which is kind of like a car engine's piston. Super efficient, but it can be a bit high maintenance. Then you've got the rotary screw. It's compact, gives you a nice smooth output, but it can be less efficient if you're not running it at full load. But wait, there's a third major player on the field, the centrifugal compressor. As you can see, this is a dynamic machine, totally different from positive displacement. And here's the absolute game changer for Alex. Highlighted right there in that second point, it is inherently oil-free. By its very design, the lube for the drive system is completely sealed off from the air. This makes it a really, really strong contender. Right. Given the whole contamination crisis, making sure the air is clean is now Alex's #1 priority. This isn't just a nice to have. For a food-grade application, it is completely non-negotiable. So that leads us to our next section. Let's really dig into what oil-free actually means. It's a simple definition, but it has huge implications. In industries like food processing, pharmaceuticals, or electronics manufacturing, any contact at all between the product and lubricating oil is just unacceptable. An oil-free design physically prevents this from ever happening. So here's a look at how they're actually built differently. On the left, you've got the old, lubricated design that caused all the problems. But on the right, the non-lubricated version uses cool materials like Teflon for the piston rings. But the real key feature is that thing called a distance piece. It physically separates the oily crankcase from the compression cylinder, making it literally impossible for oil to travel up the piston rod and into the air. Okay, armed with all this knowledge, Alex puts together a final checklist for the new machine. Number 1, air quality. Must be 100% oil-free, no exceptions. Number 2, capacity. This time it's sized for the real demand, plus a buffer for future growth. And since this new machine will be a base load unit running all the time, full load efficiency and reliability are critical to keep those operating costs down. And here it is, the final choice. Alex selects a crosshead type reciprocating compressor. Now, this design offers the best of both worlds. You get the high efficiency of a reciprocating machine, but it's combined with that non-lubricated distance piece design that guarantees 100% oil-free air. It's the perfect blend of efficiency and purity for this job. And with the new compressor installed and the major leaks repaired, the outcome is a total success. The system pressure is stable, even during peak demand. The product integrity is completely secure. And most importantly, the factory is back up and running. A major crisis was averted through methodical, solid engineering. Alex's story is a perfect case study of how you should diagnose these problems. And it also brings up some of the most common questions that engineers like you face all the time. So let's use what we've just learned to answer them directly. This is without a doubt the most critical question. Getting this wrong was the root of Alex's entire problem. So how do you get it right? Well, it really just boils down to following the exact process Alex did. You have to account for every single device, calculate their consumption, apply a realistic load factor, and then, and this is so critical, you add a margin. A 10% buffer for existing leaks is pretty standard, plus you always want to plan for future growth. Don't size for today, size for tomorrow. The next big question is all about air quality. If you absolutely, positively cannot have oil in your system, what are your go-to options? Here's the straight answer for you. Centrifugal and liquid ring compressors are, just by their very nature, oil-free. The air never even comes close to the lubricant. For the other big types, reciprocating, screw, and lobe, you have to look for specific non-lubricated or oil-free models that have special design features, like that crosshead design Alex chose. And finally, let's talk about money. Where do most compressed air systems waste the most energy without anybody even noticing? You know, this quote from our source material just says it all perfectly. It's not about some massive pipe failure, it's death by 1,000 cuts. The single biggest hidden cost in almost every compressed air system out there is the accumulated waste from dozens or even hundreds of small, undetected leaks. So we'll leave you with this question to think about for your own system. Just because your compressor is running doesn't mean it's healthy. Is it meeting your demand efficiently? Or is it like Alex's old machine, just working overtime to pump expensive, compressed air out of 100 tiny holes, running up a massive energy bill in the process? If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together, stays together.